So have a look here at the first question. This is from 2021. The question says a mantle source rock melts at a time T naught, giving rise to melt M and residue R. Okay, which of the following statements is correct about evolution of the ND ratio and SR isotope ratio basically in melt? So M is the melt that crystallized to form a rock, and R. So it is asking in both, like evolution of both these ratios in melt and also in the residue. So firstly, try to understand a basic concept before we jump onto the question. What happens is there is a source rock. Okay. Whenever this source rock melts, let's call it as S. Whenever this source rock melts, let's write it melting. It gives two things, or we can say it gives two products. One is upon melting you get the melt, obviously. Okay. And the other one is residue. Residue is the remaining solid part which didn't melt. Okay. This residue is nothing but remaining solid part. Remaining solid, we can write remaining solids. Okay. Now this M, the melt that has been formed from this source rock upon melting, this M is responsible for the formation of magma. Like this is a part that forms magma. Okay, this melt itself, we can say that it itself forms a part of magma, which in turn crystallizes to form a rock. Okay, so I will simply write it as rock. So this magma in turn, upon cooling, now after melting, with time there will be cooling. So upon cooling, this melt that is a part of magma, it consolidates itself into a rock, or it crystallizes itself into a rock. Okay, so this is the basic thing that happens upon melting of a source rock. So this is the first thing that you need to know. Then let's see at both the isotopic ratios one by one. So firstly, uh, what kind of reaction do you expect over here? Anyone? Does anyone have any idea about this?
So samarium 147 will give 143 nudium, and rubidium 87 will give strontium.
Right. So there is SMND reaction and RBSR reaction. Okay. So as you rightly mentioned, SM gives ND and rubidium, that is RB, gives SR. Okay. So we won't focus on that reaction part as of now. Let's just go through the question once again, what it is asking. A mantle source rock melts at a time T naught, okay, giving rise to melt and residue. So at time T naught, it is melting. So let's write it here at T is equal to T naught. So at T is equal to T naught, melting event happens, okay. Let me separate this part. And then it produces melt and residue. Which of the following statements is correct about evolution of the ND ratio and SR ratio in melt and residue? Okay, let's have a look at the options, what it is given, then we will discuss this a bit. The first option is given as the growth of ND isotope ratio versus time is faster in residue than melt, and the SR isotope ratio grows slower in residue than melt. Okay, so it is basically saying that strontium ratio, isotopic ratio will behave in exactly the opposite manner in which ND isotope ratio is behaving with time, okay, upon melting. So one thing that you need to understand is, firstly, you also need over here to know what is incompatible and compatible elements, okay. Can anyone tell me the definition of this?
The compatible elements have the more affinity towards the crystal phase, and incompatible elements have less affinity towards the crystal phase, or they have more affinity towards the melt phase.
Right, actually, I think the screen is not visible now. It should be visible again. Okay. So basically, like in basic terms, if we talk about incompatible and compatible elements, so what happens is, in a crystal structure in any mineral, let's say K feldspar, okay? Let's, for example, just take K feldspar and olivine. Let's talk about two examples. Now, if we substitute any cation from K feldspar has potassium, aluminium, and Si, right? Similarly, what does olivine have? It can have iron, it can have magnesium, it can have Si. Also, there are different varieties. So I am just mentioning the common ones. K feldspar has only this one. This can have different varieties as there is a solid solution in between. So here, if I tell you there is an atom which has an atomic radii way too bigger or way too larger than these elements. Now let's say K, Al, each of them are like this in comparison to this one. So what do you think, in a rock that is constituting of these particles, can this particular atom have its own space over there in that rock? Can it easily accommodate in that particular rock?
So it actually depends upon the structure, like the atomic space, whether it can be, whether it fit into it or not.
Right, but here, if I am talking about, if all the other atoms that constitute a rock are way smaller in comparison to a particular atom that we are trying to fit in that very rock. So what happens here is, let me just clear it out. Whenever a particular atom tries to fit in and it cannot just simply fit into a rock, that particular atom is known to be incompatible, or that particular element is known to be incompatible. You must have heard this word compatible, right? What does compatible mean? It simply means any two things can easily be together. Okay? So incompatible elements are those elements which cannot easily fit into any common rock forming mineral, we can say. But on the other hand, compatible elements are those elements, those can be fitted into common rock forming minerals. So this is the basic idea that in layman terms, basically. So you can talk about affinity and everything. There are many things that you can talk around this, incompatible and compatible. But the basic idea is, whichever element you can think of fitting into common rock forming minerals or common areas, those are compatible, and whichever elements are not easy or cannot be fitted into any such kind of minerals or rocks, those elements are incompatible. Okay, so this comes from the basic definition. So in the, we have two reactions over here, RBSR. Just 1 second. I won't write the complete reaction. We just need to understand the concept and a few things we need to remember here. The question would be solved automatically. So in this, between these two, which one is more incompatible?
RB.
RB. Yes, right. RB is incompatible here. Okay. And if we talk about SMND, the other reaction, then which one will be more incompatible?
ND.
Yes, right. Here, ND will be more incompatible. Just to give you an overview, I have also attached a periodic table over here. Now have a look where these four elements are. Okay. RB is here. SR. Alright. Here you have SM. Here you have ND. What relation do you think, if you know the basics of periodic table, what relation do you draw from this particular periodic table according to the placing of these elements in terms of, let's say, atomic size? Can anyone tell me?
It's increasing from left, right.
Yeah, so can you tell me, as they are placed in the periodic table, can you tell me why RB is more incompatible, and when it comes to SMND, ND is more incompatible? You can see RB and ND both lies to the left, right? SM and
Yes, sir.
SR both lie to the right. Okay, someone is joining.
Sir, SM and ND is incompatible due to the lanthanide contraction.
Yes, actually that's one of the most prominent reason, but it also, like, it is derived from the definition of incompatible and compatible. That is why we are here. Actually, both are incompatible, but we are talking here which is more incompatible, because that determines what will happen after melting, which will have more influence either on the melt or on the residue. So which will go more towards residue, which will go more towards melt. So everything is like, the dots are connected. Everything is connected. Okay. You need to know what is incompatible, compatible, how those, which one is more incompatible. So these things are there. So okay, coming back to these equations, individual ones. We have two ratios. Okay. Now we have to look for melt and residue. Let's say here we have ND 143, 144. This is giving, producing melt and residue. Okay. Here we have SR 87, 86. Now, if you all have ever seen the graph, there is a graph for each dating method. So you must actually know about these graphs. If you are appearing for gate, these things are important. These are not that important for JAM, CSIR. Even in CSIR, like these things, the questions directly come based on graphs. Okay, for these isotopic ratios. So here, let me just draw for RBSR first. We'll take on one by one. RBSR, I mentioned that this is more incompatible. So this is the time. This axis represents the time, like with increasing time, how the melting phase behaves. So this is that output. And here on y-axis you have SR ratio. Okay. Oh, this is 86. Now at t is equal to t naught, let's say it's here. Let's say this is t is equal to 0 actually. At t is equal to t naught, melting starts. Okay. So in the question as it is mentioned, at t is equal to t naught, melting starts. The graph goes somewhat like this. This is the point, let's say, where melting begins. This is t is equal to t naught. Now what will happen? This would have been the normal case, but what happens is the graph proceeds in two directions. One is like this and one is like this. Okay. Can anyone tell me which one of this line represents the melt and which one represents the residue? When it comes to RBSR, it will differ in both the cases because in one the product is more incompatible and in one the reactant is more incompatible.
So the top graph will be the enriched one, and the bottom line will be the depleted one.
Right? So enriched one is the melt one. Okay.
Yes, sir.
Yes. This will represent the melt and this will represent the residue. Why? Because this now see here with RB, as soon as RB gets consumed, like as RB starts getting consumed, starts getting melted, more SR will form, right? Now since SR is less incompatible, RB is more incompatible, where would RB fall? Will RB contribute more to residue or will it contribute more to melt?
Melt.
RB is more incompatible. Keep this thing in mind. So, like, what is the chance of having an incompatible melt in, not melt, incompatible element in melt or in residue? Like, where the high chances are? How melt and residue have come, this you need to keep in mind.
So melt will be enriched with incompatible element.
Hello? Okay. So, also one more thing, just to make it even more clear. What is the dependency of rate of decay? Like, what is the relation between rate of decay and amount of parent? If you increase the decay rate, what will happen to amount of parent?
It will decrease.
And amount of parent is directly proportional to amount of daughter or inversely proportional. These three relations are important. You all tell me, is it directly or inversely proportional? these things will come again and again in radioactivity. Like this is a part of isotope geology, this particular question, and these things will come there over there again and again. One thing I would recommend you all to remember curves for isotopic ratios versus time, like this one. This is for SR. Okay, so remember, just try to remember these curves if possible, because if you remember the curves, it will be really beneficial to you all during exams. It can be like if a question comes from this part, it can be really beneficial to you all. So okay, this thing, rate of decay, if you increase the rate of decay, if you start decaying it a lot faster, if you start decaying the parent a lot faster, what happens is amount of parent actually decreases with time. Okay, so this is inversely proportional, and then rate of decay is actually directly proportional to amount of daughter. So basically amount of daughter will increase, right, if you increase the rate of decay. So here the direct relation is there from RB to SR. If RB is decreasing, SR will increase. That's a basic thing, everyone knows about this. Since RB is more incompatible, it will be enriched in melt. It won't form a residue, right? So we call this as enriched mantle, and we call this as depleted mantle. Now in the graph of SMND, this will absolutely reverse this case, because there ND is the one that is more incompatible. Now if we talk about SMND here only quickly, samarium gives rhodium. So here this is more incompatible. Its graph, if we draw, on 44, this is time. Okay, this will again start like this. If the melting wouldn't have started, this would have gone like this, but after melting, this ND has two variations. Okay, this ratio particularly, which time it is increasing in some part of the product, and which time it is decreasing in some part of the product. Okay, the rate of increase is low, we can say this. It may not necessarily be decreasing, but the rate of increase will be really low as compared to the other part. So in this part the rate of increase is high. This part actually starts having more and more ND as the reaction proceeds with time. Okay, so what will be this part in this particular one? This will be actually residue here. Are you all understanding this? We haven't gone from like the very basic, but is there any doubt? Please ask. Because now after having these two graphs, the question is solved. You will get the right option easily. Also, let me tell you one thing. I will write it here. What is depleted mantle plus crust? Can anyone tell me? Depleted mantle plus crust. This is primitive mantle. We call it as primitive mantle. This is just a basic thing. I just mentioned it over here. Okay. So this is the graph for ND ratio. Here ND is more incompatible and SM-ND ratio in melt will decrease as ND is more incompatible. Okay. So SM to ND ratio in the melt will actually decrease. Similarly here in this one, RB to SR ratio in the melt will increase as here RB is more incompatible. Okay. So ratio increasing means as SR is increasing, RB is increasing to more extent. So this is what ratio increasing means. Okay. As SR increases, the amount of SR increases, RB will increase more in the melt because RB is more incompatible. Similarly, for SM-ND ratio, as ND increases, SM will increase less in the melt because here ND is more incompatible. So incompatible elements firstly contribute more in the melt rather than residue because residue is the solid left out part. Okay, since it is incompatible, it won't easily fit in, it will remain in the melt itself. So this is the basic idea. I hope this is clear up to here. Is there any doubt? Please be interactive, otherwise I wouldn't even know.
Sir, please explain about lanthanide contraction.
Lanthanide and actinide contraction actually that we will come further in some questions. Here you don't require any contraction concept over here. Those mainly depend on the sizes and the like here only incompatible and compatible is required where yes lanthanide contraction is one of the reasons why these lanthanides are incompatible. Okay, that means they don't easily fit in. It's just because they have like you can say the atomic sizes differ way too much when we compare it with the common elements that constitute a rock or that constitute a mineral. So the common elements can easily be differentiated from lanthanides and actinides both. But here as you can see, if you know the basics of periodic table, you can easily get that why RB is more incompatible and why ND is more incompatible when ND is compared to SM and RB is compared to SR. So actually in some further question it has asked about that. Let's come to the question here, what it was asking. It has asked about lanthanide contraction, actinide. So all these things we will discuss along with the periodic table. I'm thinking to have an introductory class for geochemistry for some concepts. That is what I believe those are important. If we don't go through those concepts, it would be a bit difficult to solve directly the questions. So actually this course was meant to help you all out with solving questions, the way of solving questions and all of that sort. So it obviously requires you all to have a basic understanding. But still, what I'm thinking is if someone has completely ignored geochemistry so far or has not been able to study geochemistry at all so far, then we can have that overview kind of concept thing to you people for that. So if you all say so, we can go for a conceptual basic class, maybe for half an hour or 1 hour, 1 hour class. That should be enough, where we can go through the basics of radioactivity, compatible, incompatible, a bit more. While discussing questions, we can't be like doing that. Otherwise, it would be really difficult to connect the dots. So okay, here in this question, whatever like we discussed so far, let's see if that helps in finding the right answer. it is saying which of the following statements is correct about evolution of ND ratio and SR ratio in melt and R. So how they are evolving in melt and in residue respectively. So the first option is the growth of ND isotope ratio versus time is faster in R. That means growth of ND isotope ratio is faster in residue than melt, and SR isotope ratio is slower in residue than melt. What do you think about this option? Will it be correct or incorrect?
Sir, option A.
Yes, we are discussing option A. Will it be correct or incorrect?
Yes, sir, it will be correct.
Anyone? Are others understanding these things over here? Option A, yes. So according to the graph, you can easily see that the very first option, option A, is the correct statement. All the other statements are wrong statement. Okay. Option A is saying that ND isotope ratio with time is growing faster in residue than melt, and SR isotope ratio is behaving exactly opposite. So let's see the graph. ND1 is this one. So ND isotope ratio is growing faster in the residue than the melt. So this is what we have got here, right? It is growing faster here in the residue. In the melt, it slows down. And exactly opposite is the case in SR. In SR, you can see in the melt, this ratio is evolving faster or growing faster. But in the residue, it slows down. So A option will be the correct option. So like that's not an issue. We will come back to such kind of questions again, like in future. Since this was the very first question in 2021, so I put it up straight over here. I know it can be difficult in the very first class, going into a bit of details, but still, these things will help. So okay, let's get to the next question. The next question says, now this is a simple mole concept question. You can easily expect such kind of questions even in IIT-JAM. The mole percentages of SiO2, Al2O3 and K2O in a granitic rock are 84.21, 7.89 and 7.89. Okay. The molar proportion in percentage of K feldspar in the rock is. Now firstly, how do you approach such kind of questions? What should be your first step when you see such kind of questions? This requires a bit of attention, like extra attention in terms of approaching the question. It's not that easy to go question as it seems. Why? I will tell you. So basically, whenever you get such kind of a question, always, like here it is saying molar proportion of K feldspar, right? So one particular rock is mentioned. What is the chemical composition of K feldspar? What is K feldspar formula?
KAlSi3O8.
Right? It will be KAlSi3O8. So here, what are the moles of individual these atoms or these elements? KaLSi3O8 constitutes of 1 mole of potassium, right? 1 mole of aluminium, 3 moles of Si, number of moles. Is it right what I have written?
Sir, it will be half K and half Al.
No, that is why I have put semicolon over here. I am talking about number of
Okay.
moles.
Yes,
What
yes,
you
sir.
are talking is this. Let me write that also. Half K2O plus half Al2O3 plus 3 SiO2. Now this is equal to KAlSi3O8. So here, that is why I have not mentioned here is equal to. This is, I am just talking about number of moles. In KAlSi3O8, how many number of moles of potassium is there? 1, right? Similarly, 1 number of mole of aluminium is there, 3 number of moles of Si is there, and then 8 number of moles of oxygen is there, oxygen atom. We are talking about individual atoms here. And yes, this what you were talking about, this is the thing over here. We have mole percentage of this oxide K2O, mole percentage of Al2O3, and mole percentage of SiO2. So these 3 mole percentages we have. It is asking that what is the molar proportion percentage of this. Okay, this we need to calculate. So if I talk about molar percentage, K2O is given to be, K2O is 7.89, again Al2O3 is 7.89, and SiO2 is 84.21. So firstly, what I was talking about, the very first approach should be, these values are given, right? You have a calculator in your exam. Always first calculate the ratios, in which ratio these values are given. Now quickly tell me what will be the ratio. This is 1:1:. What will be this? 84.21 divided by 7.89. What will be 84.21 divided by 7.89?
Sir, 10.673.
10.67, right? So it will be 10.67. So this should be your first step. Calculate the ratio of the given values. These values are given to you, and this will add up to 100 actually. I think it should add up to 100 because they don't give questions otherwise. Let us just add these. 7 and 14, it's around 15. Yes, it should add up to around 100. Yes, it's coming out to be 99.99, so it is adding up to around 100. Okay. So that means here you can see this is the given ratio proportion. That means SiO2 is 10.67 times Al2O3 and K2O. But in reality, what is the ratio that is required to form K-feldspar? Can anyone tell me? What will be the ratio for KAlSi3O8 to be formed? What will be the potassium aluminum silicon ratio? What is required? The required one is 1
Sir,
is to
1
1.
is to 1:3.
Yes, right. The required one is this, right? This directly comes from number of moles. 1 is to 1 is to 3 is the required one. If you get this ratio proportion for these 3 elements or these 3 compounds, you can easily form KAlSi3O8. Okay, you can easily form K-feldspar. You can't directly jump to this question. I'm telling you why. So here you can see this is the ratio required, but what we have is this ratio. So that means SiO2 is more present than what is actually required to form K-feldspar. So this particular rock, that here it is mentioned now, the molar proportion of K-feldspar in the rock. So this particular rock is oversaturated in silica. It's a silica oversaturated rock in this particular question. This rock is silica oversaturated. So you may get questions on undersaturated silica condition, okay, or on oversaturated silica condition. All right. So if this ratio would have been 1 is to 1 is to this third value something below than 3, then it would have been silica undersaturated. then the amount of silica that is required, the amount of silicon atoms that needs to be present to form K feldspar would have been less than what that is required. So that means it is undersaturated in silica. Here it is oversaturated in silica. So that means if we talk about the complete rock now, what all constituents are forming the rock? Because that is what you need to find out towards the end. You need to find the percentage of all of everything that is present in the rock. Okay. So quartz is there. There is free quartz. Okay. That got left out. Now here what will happen is when you have such kind of thing, let's say x plus y plus z producing m. Now if z is more than what is required, x and y will get consumed first. This will get fully consumed and still z will be left. So this is actually known as limiting reagent. So these are limiting reagents. These are limiting the reaction. The reaction is not getting fully completed. There is something that is getting left behind because it didn't get fully consumed. Are you getting my point? If Z is more than what is required, it will get left out. X and Y will get fully consumed. So here you have quartz 3SiO2. This is basically K feldspar. Half K2O plus half Al2O3. So this is the complete rock that we have in this case. And this particular portion is K feldspar. So now you know that quartz is more than what is required. Quartz is there in greater proportions over here. Up to here, is everything clear? Please let me know. Okay, so what the question is asking? The question is asking about molar proportion in percentage of K feldspar in the rock. So firstly, let us try to understand what it is asking. It is asking mole percentage of K feldspar in the rock, basically. So what will be mole percentage of K feldspar? If we write it in general terms, it will be moles of K feldspar, number of moles of K feldspar divided by moles of K feldspar plus, what should I write here? Moles of,
SiO2.
yes, moles of quartz. So this is constituting the whole rock. When we try to calculate mole percentage of K feldspar in the rock, we will take into account everything that is there in the rock. So K feldspar and quartz are there because quartz is left out. So it will have be in a form of free silica in the reaction, or we can say in the products. Okay. So here we have, now from here actually we will start the calculation keeping this thing in mind. If you wouldn't have taken this thing in mind, then you must have confused somewhere. You must have got confused. Okay, so if you wouldn't have had this clarity that quartz will be the leftover part and quartz and K feldspar will together form the rock. So let me ask you one question, simple question. How many moles of K in 1 mole of K feldspar that I asked previously? Now this is simple mole concept practice. Number of moles of K in 1 mole of K feldspar. What will be the value here?
1.
1. Similarly, like if you must have studied unitary method, this implies that this particular thing, that this is 1, this implies that 1 mole of K implies 1 mole of K feldspar, right? So this is the simple meaning that we can draw from it. So now how much K is there? 7.89 into 2 moles of K implies 7.89 into 2 moles of K feldspar. Why I multiplied by 2 here? 7.89 is the mole percentage given for K2O.
Because our KLSI308 made up of half K2O. So to make it 1K, so we need to multiply 2 so that half will be cancelled out and 1 will remain.
Exactly. Exactly. So this was the case that we had, right? Half K2O is forming KLSI308. Half Al2O3 is forming KLSI308. So that means for K2O we have 7.89 as the mole percentage. Now forget about percent here. Don't think in terms of 7.89 divided by 100. I should have written. Forget about the percentage. We are just, because it is adding up to 100, we can simply take these absolute values. 7.89, 7.89, 84.21. Okay. So we are just simply, number of moles is just a number. It is just representing some quantity. So if we are talking about weight, that means let's say grams. So what is number of moles? It is given weight divided by molecular weight, right? Given weight divided by molecular weight. This is actually number of moles. And I think everyone knows what is molecular weight, how to calculate. So this is just the atomic weight, summation of atomic weights of individual atoms that are present in that molecule. Okay, so if it is CO2, atomic weight of C, atomic weight of carbon plus 2 times atomic weight of oxygen. This is the molecular weight of CO2. Okay, so this is a basic idea, and let's say CO2, some weight is given. So given weight divided by molecular weight gives you the number of moles that is there. So number of moles is just a number. It is just a representation of some quantity. Here it is a representation of weight. So we will imagine that in 100 grams of, like there is in total 100 grams of K feldspar. So out of these 7.89 grams of K2O is what we have. But here half K2O is constituting K feldspar. So that means we will multiply 7.89 into 2 to take the proportion for potassium. Okay. So this is what we have got here. 7.89 into 2 moles of K now implies 7.89 into 2 moles of K feldspar. Okay. Now 1 mole of K feldspar has 3 moles of SiO2, right? 1 mole of K feldspar has 3 moles of SiO2. This also we have seen above. Here you can see 3 moles of SiO2 is there. Okay, for 1 mole of K feldspar. So number of moles of SiO2 would be, or number of moles of quartz. Why we are calculating this? Because we need it here, moles of quartz, right? So that is why we are connecting all these dots to get to there. Number of moles of quartz will be 84.21 that was there for SiO2, if you remember, 84.21 minus 3 times number of moles of K feldspar. Are you getting how this part is coming? Here it is actually number of moles of SiO2 in quarts. It should be this. Because SiO2 is there even in K feldspar and it is there even in quarts. So we are calculating number of moles of SiO2 in quarts. So that will imply directly number of moles of quarts. So still, to make it clear, I have written it in this way. Because quartz is nothing but SiO2 and SiO2 is there in K feldspar as well. So the left out SiO2 that is there in quartz, this we will calculate like this. Do you agree with this? 84.21 was the
Excuse me, sir.
total. Yes.
Sir, do we need to multiply 3 in with our number of moles of K feldspar or number of moles of silica?
Actually, this is why I wrote here the above sentence. 1 mole of K feldspar has 3 moles of silica, right?
Yes, sir.
Now see, again jump back to this reaction, this particular thing. Here what we have is this 84.21 was the proportion for SiO2. This is available, this is given. So now the SiO2 that is there in quartz will definitely be less than 84.21, right? Because some part from this 84.21 is getting consumed over here. So now what part is getting consumed over here? It is 3 moles of K feldspar, right? Are you
Yes,
getting
sir,
my
yes, I
point?
got it. Got it. Yes, sir. Yes, sir.
Okay. So basically, this portion is the part of SiO2 that is getting consumed to form K feldspar. So what part is getting consumed? 3 times, like 3 times number of moles of K feldspar is getting consumed to form K feldspar. This is for SiO2. And this is the initial one that we had. So now number of moles of SiO2 that will be left in quartz will be this 84.21 minus 3 into number of moles of K feldspar. Don't confuse, these are actually easy concepts. These take time to, like, you need to go through this particular solution 2 to 3 times. Then you will automatically connect the dots, you will automatically get things. Because maybe right now you are not in touch with mole concept, you have forgotten each and everything. All these things are quite basic. Like right from the reaction, you can determine each and everything. What number of moles of what part will constitute what other another parts, all these kind of things. Okay. So just focus for the moment and then go through these solutions once again by your own. Give it time. So here what we will have in calculation 84.21 minus. Still, I hope some people must have got what I am telling over here. Minus, we will have 3 times. What is number of moles of K feldspar? We just calculated here. We will put 7.89 into 2. Now do this calculation and let me know what is this coming out to be. 84.21 minus, it will be 6 times 7.89.
Sir,
Sir,
36.87.
36.87. Okay. So this is coming out to be 36.87. Now 36.87 is the number of moles of SiO2 that got left. Okay. After forming K feldspar. So this is constituting quartz in the rock. So here, okay, let me add one more page. So here we will go back to this, what we wrote, what is required, this part. This is what the question is asking. Mole percentage of K feldspar is equal to what we have got? Moles of K feldspar divided by moles of K feldspar plus moles of quartz, right? So now we will have, therefore, mole percentage, here it was mole percentage of K feldspar number of moles of K feldspar we will start with in these questions. What happens is, why we have started with 7.89, we will always start with the limiting reagents, like those are getting consumed up. If you will start with silica, if you will start with 84.21, it won't take you anywhere, because there is some value that is remaining out of that. Plus here it will be 36.87 into 100, since it is asking in percentage. So now just quickly let me know what will be the answer. This will be the answer. I will just quickly repeat this complete solution once.
So 29.97.
29.97. Okay. Just let me quickly check the answer also. This is question number 43. Question number 43, 2021. They must have given in some range, that is for sure. In numerical type, mostly whenever the integers are there, they give answer in some ranges. So okay, the range is 29.9 to 30.1. The official answer key has 29.9 to 30.1. This is the range. So this is perfectly lying within the range, right? Did it ask up to 2 decimals? It is asking round off to 1 decimal only. So when you round off to 1 decimal, actually this will become 30. Is it true? That is why this is the range that they have asked. Did you get the approach of such kind of questions? You need to even think a bit. It's not like you got some mole percent, like there it is already given for K2O, Al2O3, SiO2, and then you start calculating accordingly for K feldspar. You can't directly get it. Here you can see like it involved a bit of thinking, but eventually what I would say is it's a bit of a like simple solution itself, like not that complicated. You just need to go through it twice or thrice on your own, then you will definitely get this, what all things are connected over here. So firstly, see, just quickly going through this. Whenever you get such kind of question, these kind of questions are quite probable. As I mentioned, in CSIR, in JAM, in GSI pre, it's not that probable, but in CSIR, in IIT-JAM, in GATE, it's very much probable that again you will get such kind of question. At least one for sure. The mole percentages of SiO2, Al2O3, K2O in a granitic rock, these are given. Okay, mole percentages are given. So firstly, you need to have a look at the ratio in which these mole percentages are given, and then compare it with the product. It is saying that the molar proportion of K feldspar in the rock is, So basically these three oxides are forming K feldspar. Okay, here we have written in a reaction form half K2O plus half Al2O3 plus 3 SiO2 gives KAlSi3O8. Everything is perfectly balanced in this reaction. Okay, and we have got K2O mole percentage, Al2O3 mole percentage, SiO2 mole percentage. KAlSi3O8 mole percentages, it is asking what will it be in the total rock. Okay, by simply looking at the formula of KAlSi3O8, at the formula of K feldspar basically, you can say that 1 mole of K is required, 1 mole of Al is required, 3 moles of Si is required, and 8 moles of O is required. So forget about O because O separately is not mentioned over here. Here the cations are already in oxide forms, like it is silica, alumina, and potassium oxide. So 1 mole of K is required, 1 mole of Al, 3 moles of Si. The ratio is 1:1:3, that is required to form KAlSi3O8. But when you calculate the ratios that is given in mole percentage, that comes out to be 1:10.67. So this ratio is a lot. Like this ratio simply determines that silica is way more in quantities than what is required to form K feldspar. That means silica will remain unconsumed even after the completion of the reaction to the formation of K feldspar. So silica will consume itself up to an extent of what is required. The extra silica will remain as free silica or in form of quartz. So basically the rock is now having quartz and K feldspar both. Okay, so this is what we derive by comparing the ratios. So this part gets important. Whenever you have these given values, first calculate the ratios, whether it is more than what is required, whether any compound, or whether any compound is less than what is required. Here it is more than what it is required, so it is silica oversaturated rock. If silica was lesser, it would have been silica undersaturated rock. Okay, then we start calculating what is required in terms of value. So here, this part now we know that rock constitutes of quartz and K feldspar. Okay, then this is what we require, mole percentage of K feldspar. Now mole percentage of K feldspar, where it is asking in rock. So K feldspar is being compared to everything that is there in rock. So this will simply be number of moles of K feldspar divided by moles of K feldspar plus moles of quartz. This quartz is unconsumed quartz. Don't mistake it with the quartz that is included in K feldspar. This quartz is totally unconsumed quartz that is left behind. Okay, so that is forming the other part of the rock. So this denominator represents the complete rock. So this is how we get the mole percentage of K feldspar in the whole rock. Then step by step we try to calculate the denominator basically. What is the number of moles of K feldspar in this rock? What is the number of moles of unconsumed quartz in this rock? Okay, so if we get these two values, we will get the answer. What is the mole percentage of K feldspar in the whole rock? So how we are getting to that is step by step. Now number of moles of K in 1 mole of K feldspar is 1. Okay, if we talk about 1 mole of K feldspar, it is having 1 number of moles of K, 1 number of moles of Al, 3 number of moles of Si, 8 number of moles of oxygen. When we talk about 1 mole of K feldspar, then we have 1 mole of K implies 1 mole of K feldspar. This is pretty obvious from the previous sentence. Number of moles of K in 1 mole of K feldspar is 1. That means 1 mole of K is there. It is implying that 1 mole of K feldspar is there. If we know that 1 mole of K is there. Similarly, it could be N actually. If N moles of K implies N moles of K feldspar. 2 moles of K implies 2 moles of K feldspar. Likewise. Okay. Then we try to get the number of moles of K value. Now how do we get this? Why we did this? 7.89 here is the given molar proportion. Okay, so given molar proportion for K2O is 7.89, but K2O is getting half consumed, like half K2O is there in the reaction to form K feldspar. So we'll multiply it by 2 to take full account of K2O, right? So 7.89 into 2 moles of K implies 7.89 into 2 moles of K feldspar. This is pretty simple from the above part. This is simple unitary method that you must have studied during your childhood itself. Then we come to, now we have got number of moles of K feldspar that is there, okay, in the rock. This we have got. Because in the rock, this is the number of moles of K. So the number of moles of K is exact equivalent to number of moles of K feldspar. So this is the number of moles of K in the rock. This is given to you in the question. This is what we have got according to the direct implication. Number of moles of K feldspar we have got. This is the first part. Then we have 1 mole of K feldspar has 3 moles of SiO2, right? Again, from this reaction, 1 mole of K feldspar has 3 moles of SiO2. Then we have number of moles of SiO2 that is there for quartz. That means number of moles of SiO2 that is unconsumed. So 84.21 is the given molar proportion of SiO2, total SiO2 that is there. So we will subtract the number of moles of SiO2 that is getting consumed to form K feldspar. Okay, we will subtract that from the total proportion, then we will get the unconsumed part, right? So we will subtract the consumed part. So here this bracket is the consumed part. 3 times number of moles of K feldspar. So this much SiO2 is getting consumed to form K feldspar. So by this we get the unconsumed molar proportion of SiO2 to form quartz, the free silica. So then the calculation is pretty simple. So this is the answer. Now did you get it? Like I have tried my best, whatever I had, the energy. Please let me know, whoever is attending, did you get this? This is important. If you get the way of solving this, if you connect the dots from the first step to the last step, you can get easily any question right whenever you see these kind of questions. Okay, I think some people have got it. Okay, so we will move ahead. We already spent a bit of time here, but this will help because again we will get some questions on mole concept. Then it will be easier for you all to understand who are still connected. Okay, who are still connected in terms of understanding things. If you didn't even understand so far, try to solve these questions on your own. Try to play around these questions. Try to give it time so that when you come out with wrong, illogical values, you will automatically understand how these things are working. Okay. So, okay, next question we have here is a rock formed at time T naught is equal to 0 with number of carbon atoms C14 is equal to 10 to the power 5. Okay. So, number of C14 atoms, I'll write it here. Is equal to 10 to the power 5. This is at T naught is equal to 0. The number of C14 atoms, it is asking in log 10, okay? So basically whatever value you get here, you have to take log base 10 of that value. So let's say this is x. The question is asking about log base 10x, okay? So here it is saying, clearly mentioned in log base 10. After a time of, now here t is, here it was t is equal to t naught is equal to 0. Here t is equal to 8 into 10 to the power 3 years is dash. So number of C14 atoms after this much time, what will it be? At t is equal to 0, it was this. At t is equal to some given time, what will it be? They have already given here, use a decay constant of, that means decay constant is lambda, okay, 1.25 into 10 to the power minus 4 per year. Round off to 3 decimal places. Okay, so firstly, let us see here. Let's say there is a parent rock, okay, parent radiogenic rock, radioactive rock, as N. Now it is getting decayed into forming a daughter, okay, forming a daughter. We can also write it as, earlier it was N naught, now it has become N with time, okay, after time t it has become N, right? We can write it in different forms. So here what do you reckon from here? If we talk about dN by dt, that is decay rate with time, what is the change in dN? That means basically what is the change in n? D itself signifies change, that is delta. So n, what is the change in n? N is the number of parent, okay? So what is the relation here of this with direct n? Can anyone tell me here? Or we can say n naught, the initial one. Any relation over here? Anyone? It will be directly proportional, right? And here there will be a minus sign. Why minus? Because with increasing time, n is actually decreasing. So this is a reverse situation. So we put a minus sign. With increasing time, n is actually decreasing. Okay. So you must actually, if we derive it from here, we take integrals and all. So this equation comes out to be n is equal to n naught e to the power minus lambda t. You must have heard about this. Lambda is nothing but the decay constant, this proportionality constant. Okay. So here this is given lambda, decay constant. Okay. This is one formula. You must remember all these formulae. We will discuss whenever these come in questions. So here we have this case. Let's try to solve this one quickly. What can I write over here? N is equal to n naught e to the power minus lambda t we have. So n is equal to, what is n naught in this question? What is n naught in this question?
10 to the power 5.
10 to the power 5. N naught is 10 to the power 5. Okay. E to the power minus lambda. So minus lambda is 1.25 into 10 to the power minus 4. 1.25 into 10 to the power minus 4. What is t? T is this, 8 into 10 to the power 3. Here you can see per year and year will get cancelled out. Okay. T is 8 into 10 to the power 3. 8 into 10 to the power 3. So all this is going in the e to the power, basically power terms, e raised to this particular part. Okay. So this is what we have got, and it is asking about n itself. So this is a simple direct formula question. It is asking about n, okay, where this will be n, and then we have to calculate log base 10 n. So now here what are you getting here in e to the power terms?
It would be e to the power minus 1.
Right, it will be e to the power minus 1. If you calculate this particular bracket, it will come out to be 1. Okay, so it will be e to the power minus 1. That means n is 10 to the power 5 divided by e. So now let's take log base 10 both sides, because that is what we require. That is why it is asked in log base 10, because it is coming out to be in this form. So on both sides, if we take, here it becomes log base 10n. This we need to answer, okay? Log base 10n is equal to, do you know log properties? Like up to some extent, everyone should know log properties. This division 1 gives negative, right? Log base 10, 10 to the power 5 minus log base 10 e. Okay. Again, this 5 will come out, right? It will be log base 10, 10. So this will eventually be 1. Because whenever there is something of this sort, log base a, log base a of a, so this comes out to be 1. Okay. So whatever you put at a, this will come out to be 1. So there are some properties over here that is included. I will discuss the important ones, whichever is required. Now, what is log base 10e? This will be 5 minus log base 10e. What will be log base 10e?
So 0.434.
Yes. So this will come out to be 4.567 we can write to round off. 4.567, okay? Right? They have asked up to 3 decimal places. So this is what we are getting here. 4.567 up to 3 decimal place. Now here, remember one more property of log. ln is different and log base 10 is different. Okay. ln, yes. ln is nothing but log base e. Okay. And also ln is equal to log base 10 into 2.303. So you can remember these little things. So how this will imply is, if ln2 is there, ln2, this means it is 2.303 into log base 10 of 2. Did you get this point?
Yes.
Hello? Is someone saying something? Okay, so I think you must have got this point. This was basic. So this question is also done and dusted, right? I don't think there should be any problem with this question. This was a basic, easy question. There are numerous ways to solve these kind of questions. You can have numerous ways. You can calculate the amount after each half-life. Okay, even you can do that. So it totally depends on you, how you are seeking to like proceed with these questions. I can like mention some variations over here. Just let me mention here itself. So okay, n is again equal to n naught into half to the power small n. What is this small n here?
So number of half-life.
Yes. So I'm just writing some basic formula here. Okay, so simply we can write half-lives only. Number of half-lives. So this is one. So this you can use. Here you have actually flexibility to use many kind of formula and many kind of equations. It's just that you need to be precise in picking up the formula that will take you less time. There are some formula if you use them, even using them can take you to the answer, but it will take more time, more calculation time. So you need to be precise which formula you have to pick up. Okay. Then you have T half. T half is ln2 by lambda, right? This in turn is 0.6932 by lambda. This is T half. What is n number of half-lives? Given time divided by T half. Okay. This is how you get this small n, number of half-lives. Let's say given time is 8 years and T half is 2 years. After every 2 years, it is getting half. So number of half-lives here would be 4 for a span of 8 years. Okay. So remember this also, it sometimes helps. Directly there is some given time and half-life is given. So you can easily calculate n, and then either n naught is given or n is given and the other one is asked. So you can use these two equations and easily get to answer for some questions based on these. So there are questions like these, like some specific time is given, T half you know, okay, or you can say lambda you don't know T half, so from lambda you can calculate T half. Okay, given time is there, so you can calculate now small n, and then using small n you can calculate this n. So there are numerous ways as you can see here. Now even lambda t is given, you can directly use this equation instead of using all these three, all the other three. Okay, so let me write it here. This is 1 2 3, these are used frequently together, and then this is a. Let me write this equation as a. This can be used alone at times, but this equation sometimes gets a bit lengthy when you substitute e to the power something, and here fortunately we got the bracket terms was exactly equal to 1, so it was easier. Otherwise many a times you may have lengthier calculation in this particular a equation. Okay, so it's better sometimes to use the combination of these three, 1 2 and 3, to get to the answer. So these are the basic equations that we use. There are some more like that, those are that depend on daughters. Like if we say daughter product d naught plus n naught minus n, this is one equation. Okay, how did this come? This come like this, n naught gives d naught, n gives d. So basically this is at time t naught, this is at time t. Okay, so from here if you see this d, what can we write in place of this d? This is nothing but d naught plus the basically the decline factor between these two, and not to n. How much this has declined will get added to d naught, right, to produce d. So I think this you can get it. This is simple math. So with this we get this one, d is equal to d naught plus n naught minus n. Now here you can see this d naught is basically the non-radiogenic daughter. Non-radiogenic. Non-radiogenic means that daughter part which is not produced because of radioactivity. Okay, and this part is the radiogenic daughter formed, because at T is equal to T naught there was already some D naught present over there. When actually the radioactivity or radiogenic activity started, during that time there was already some D naught present. So that D naught is actually non-radiogenic. It is not produced via radioactivity. Now this part n naught minus n, this is basically the radiogenic part. Okay. So this final D actually includes both this D naught that was there at T naught and then this particular n naught minus n. I hope you get this. This was a bit tricky and this is a bit important one. I hope you all get this D part and all these basic equations. Just text for once if you all got this. Okay. So yes, this daughter part and all this was a bit important. So okay, moving on to the next question. We will keep on getting such kind of questions. As you can see, this document is of 88 pages. You can see over here towards the right top hand side. I have compiled all the questions. Like for past 2 days, I was doing this. Whenever I got time, I compiled all the GATE and radioactivity JAM questions as well to form this document. So this document has geochemistry and radioactivity complete previous year questions. So 88 pages are there. There are n number of questions. Like we can keep on solving them. So that is why I said it will take around 4 to 5 classes, but it would be enough and like it would be worthy for you all. Moving on to the next question, we'll keep on coming on such kind of questions, whatever we have discussed so far today. Thus the forms changes, the question remains the same. Here the heat flux at the Earth's surface is 60 milliweber per meter square. If the thermal conductivity at the surface is 2.5 Weber per meter per centigrade, the geothermal gradient is in degree centigrade per kilometer in integer. Now in these kind of questions, as I already mentioned during hydrogeology, sometimes you can directly use unit and dimensions if you don't know the formula or anything. So let's see if that approach works over here. Sometimes this approach doesn't work because there is some constant as well in the formula that is multiplied. Okay. So because of that constant, this sometimes cannot work, but sometimes these definitely work, the unit and dimension method. Here we have unit as one unit is milliweber per meter square. Okay. Second unit is Weber meter per degree centigrade. I will tell you the formula, but first let's see. It is asking in degree centigrade per kilometer. Okay. So what do you derive out of these two units? What shall we do with these two units to get this? Anyone?
If you will take the ratio.
Yes, if we take the ratio, right? So basically this should be in numerator, right? Here it is degree centigrade per degree centigrade. But here we require degree centigrade, like here it is in numerator. So if this two come in numerator, this whole should be in denominator. So let's see now. Let's just divide this like this and see if we get it. This Weber will get cancelled actually. Okay. Milli will be left. So remember that milli part is basically 1,000th part. Meter. So okay, I'm just doing the reciprocal of each minus ratio. Here m minus 2 will become m square in the denominator and this will come above degree centigrade. So this meter, it will cancel out this, and now 1000 into meter is, it will be 1000 only, right? Milli, Are we missing something? Actually, it has come to this form. Okay, it doesn't matter. That is the value. So forget it. So now this has come to temperature by distance form or length form, and this is what it has asked. So you could have simply taken a ratio of this 60 divided by 2.5. So you would have got the answer straight away. So now this was unit methods basically. Let's see the direct formula. The heat flux is given by H. Heat flux is the amount of heat that is passing through a particular given area. Okay, that is why it is per meter square, because it is per unit area. So heat flux is given by lambda dt by dz. This is the equation for heat flux, thermal conductivity and geothermal gradient. Here lambda is thermal conductivity, okay. dt by dz is the geothermal gradient. Gradient always means any particular parameter taken over a length. Okay, so dz is the parameter of length, distance, and T here is temperature. So geothermal gradient is basically temperature parameter over a length. Okay, measure of geothermal means basically measure of temperature, Earth's temperature basically we can say. Okay, since it is asking Earth's surface, and geothermal is used for Earth, inside Earth. So now just simply put the formula. This is an easy formula actually. H is equal to lambda dt by dz. So here also you can see H is given as 60 is equal to lambda is given as 2.5 into dt by dz. It is asking this complete value. Okay, geothermal gradient, and this is in degree centigrade per kilometer. So obviously here is temperature in centigrade and Z in kilometers, that is length parameter. So again simply you just need to divide these two values, 60 by 2.5. Take care of the units because that will make a difference in the final answer. Equals dt by dz. So here actually no need to write centigrade per kilometer still. So what is 60 by 2.5?
So 24.
60 by 2.5 is 24, right? I don't know, like I don't directly know, but yeah, like you can do it from here. If we remove this point, it will be 600 by 25. Okay, like this. Right, be 24. So okay, it comes out to be 24, but what we need to additionally multiply over here, just have a look at the units, what units it has given.
Sir, we will not multiply anything because the milliwatt 1000 will be cancelled by the kilometer one, kilometer 1000. That will get cancelled.
Right, because here in one side it will be in meter and in other side it is asking in kilometer. So when you convert that, here actually if I write 24, this milli actually that is Weber, I guess, WEBR. This milli Weber would be 1 by thousandth part, right, is equal to, but also we have meter. Where meter would be left? Meter would be left in the denominator, right? So 1 meter is equal to how many kilometers? 1 by 1000 kilometer. So again 1 by 1000. So this 1000 will get cancelled eventually. I hope you are getting this. This is an easy one. We'll be left with 24, and this is asking in integer 24. So don't get confused over here. Here actually in denominator 1 meter term will be left, and in the numerator it is MW. So WW got cancelled, so milli got left, and here this meter got left in the denominator. So this will get cancelled out when you convert meter to kilometer, because it is asking in kilometers. I hope you have got everything, whatever we have discussed so far. Now it's up to you. Shall we continue today? Like right now? If you you all are feeling exhausted, or if it is too much to consume in a single day, we can have a class tomorrow as well. We will have, like, definitely, but whether to continue for a couple more questions or 3 more questions. Just have your say. Sometimes it feels more overwhelming to consume a lot of information at one go. Geochemistry is that part where if you focus a bit, I don't think you must get any question wrong. You just need to remember certain things. You need to know from where questions are coming. So this particular document will definitely give you a broader idea what exactly the things are in geochemistry that you need to know. Okay, so this complete document that is of 88 pages right now, and it will increase, I guess, up to 120, 130 pages maybe, because we keep on adding pages while discussing some topics at length. So this particular document I will upload towards the end of the course, towards the end of the geochemistry course basically. When we move to the next topic, this particular annotated document I will upload. Okay. So please go through the annotated documents. What that annotated document will give you in return is, it will give you an exact idea, like what all things that you need to know for that particular topic, because all these things are previous year questions. Like, these are the bible. If you are going to appear for gate, there is no better practice than solving previous year gate questions, because those are directly asked by the same IIT professors. As you may be knowing that in IITs there are professors working for like n number of years. There are senior professors, so those are the panelists whenever some IIT is organizing gate. So those senior subject specialists are basically the part of the panel that decide the questions, which question would be coming in the exam. They have a pool of questions obviously, but in that, eventually none of them know which question will be there in the paper, but they are a part of forming that pool of questions. Like for geochemistry, any geochemistry veteran professor will give out around 20 to 30 questions to the panel. He will submit it. No one of the panel knows exactly which question out of his pool went into the actual exam paper, but the pool of questions is submitted by themselves. They themselves do it. So basically, in all the previous year questions, when you go through, this is the reason why the form of question changes. But many a times, what we see is, what the question is demanding out of you is mostly the same. The concepts that you need to know, the formula that you need to know, the way of solving. Connecting the dots is really important in numericals. If you don't know what is the first step, what is the first thought that should come to your mind, you may get confused many a times. That what is this question asking? I don't get it. I don't get the language of the question. So these kind of things may pop up into your mind. So just to get rid of that, you need to know the exact way and the exact approach to solving questions. Apart from that, it's pretty like easy peasy kind of thing. Like, it's not that big a task to score good marks in geochemistry. Okay. They ask a lot of numericals. As you can see on the screen right now, it is about Faraday constant, Faraday's law. Okay, Nernst equation. So this is what we call Nernst equation. So this question is directly based on Nernst equation. So if you have gone through the EHPH diagram, EHPH, basically electrode potential and all these kind of stuffs, you must be knowing what is Nernst equation. So if you know the way of solving questions, you can easily solve this question. This question is a real easy question. Everything is given. You just need to put the values. That's it. And you will easily fetch 2 marks. But what happens is many people, they leave many parts while preparing. They think that this seems to be a bit hard, uh, and then they keep on procrastinating. Like, I will study this tomorrow, I will study this tomorrow, and that tomorrow never comes. So this is the purpose of this course, this very course. If you stay till the end, if you attend all the classes, uh, like as I mentioned previously as well, even if I make mistakes somewhere, you need to point that out. That will show that you are equally involved, and that will enhance your confidence only. It won't give in return to me anything. So it will enhance your confidence only, like that I pointed this mistake out, whatever I was teaching, and then it would be more clear. It will stick with you like for longer period of time, just because of this incident, that this incident happened. So just be involved. What I would suggest is your true involvement throughout this complete course will give you a lot more than that you can think. And one suggestion I would give you, if any one of you is attending these live classes and not having pen and paper in your hand, pen and copy, then you are simply wasting your time. Let me tell you this. You are not doing anything productive. At least write down the formulae that are being used, and then in the spare time use those formulae, solve these questions again. For all the numericals, especially for MCQs and MSQs, you can write down the factual parts and then you can revise later on. But for all the numericals, if you want to ace the numericals, whatever numericals we are discussing in the classes, you have to solve them by yourself again without looking at the solutions. And if you don't get it right, then go to the solution, whatever we are uploading, whatever the lectures or PDF or anything. So firstly, right after the class, maybe on the next day, okay, just to test your memory, you can do it on the next day. Or if you want, like, both approach can be advised. If you want, you can just attempt all these questions right after the class, so that can also freshen up things. So these things you need to do. Please solve all the numericals by your own and be true to yourself during your preparation. Many aspirants, I have seen this. Like, I could easily say more than 90% of aspirants, they fool themselves. They make a fool out of themselves during the preparation. They keep fooling themselves. They keep on telling themselves that structural is my good part. I know structural. I don't need to focus that much on structural. I have been good in that. But eventually, they themselves know that when a question comes, they don't exactly remember the part or they don't exactly know the concept. So many a time, people also fool themselves that they know the concept, but in reality, they don't know the concept. They just know an overview kind of thing, and they have made themselves happy by telling themselves that they know it. So be true to yourself. Be true during your preparation. Your feedback is what matters the most. You should provide feedback to yourself that this part is remaining, this numerical is remaining, this part I have to attempt. Here, from this very portion, I have seen that questions are more probable. Almost alternate years, they are asking this particular question. So I need to know this question. For example, I would say from igneous, let's say igneous petrology. You must have seen that classification of igneous rocks is like a favorite topic for IIT professors. Or you can say a favorite topic in exams like GATE, IIT-JAM. Almost alternate year or even in succession also, in successive years, we have seen that there is definitely one question from igneous classification of rocks, like classification of igneous rocks basically. The diagrams that you see, the ternary diagrams in classification of igneous rocks. I'm not talking about metamorphic. but classification of igneous rocks, volcanic rocks, plutonic rocks. There is TAS diagram. So all these diagrams, they keep on asking questions from these. Troctolite, olivine. So these kind of things are there. Okay, verlite. So they just put the graph and then they put a question mark. Which of the following rock fills up this space? Which of the following rock belongs to this space? So these kind of questions are so common. You need to pick such kind of questions for all subjects. I'm not talking about igneous, I just gave an example. In all the subjects, whenever you analyze the previous year question papers thoroughly, you will get out, like you will be able to pick up some topics that these are the most probable ones. And the most probable topics should never be left behind in terms of scoring. You should always score out of the most probable topics. That is the way you like move ahead of the competition. You leave many people behind, because many people, they even lose out marks on those more, like as I mentioned, most probable questions. Some people will lose out marks even on igneous, like this classification of igneous rocks, igneous textures. You know that igneous texture is important. The questions are quite repeated from igneous textures. And if I talk about gate, even question from basalt tetrahedron question gets repeated. Like there are, we have seen that for past 5 to 6 years, if you compare, there are 3 to 4 questions based on basalt tetrahedron. And even in IIT-JAM, I think a couple of times they have asked this in past few years. So in this way, you need to pick up the topics, because geology is a broader subject. You will keep on studying, you will keep on reading. There are n number of things. But before going into the depth, before going into those n number of topics, cover the more probable ones first. Secure your marks up to some extent first. If those are most probable, that means 40 to 50 marks, you know that what kind of questions are going to come. They will just change the form of the question. You know that not even 40 to 50, it's actually 50 to 60, even up to 70 sometimes. There are just 20 to 25 marks of questions or 30 marks of questions that are a bit new and that are not that probable. Only at odd rare times they have asked questions from that part. Like let's say some question from sequence stratigraphy came this year, and maybe that particular type of question you must have seen way back in 2013. So 20-25 marks of the paper consist of these kind of questions, which are not that probable. But easily around 50 to 60, I can say that around 50 to 60 marks, even I can tell you the topics from where the questions are going to come. Because everyone knows, like I have been, as I mentioned, I have been mentoring for years now. So I know what are the important parts in structural geology, what actually you need to know when it comes to tackling numericals, when it comes to tackling MCQs, when it comes to tackling map based questions. Similarly in geochemistry. So I'm just going through those things. So these little things, please keep in mind. I just wanted to mention these things.